Hello, I hope you're having a great day. In this video, I will show you how ordinary and strong induction works. Mathematical induction is a proof method which can prove that some property is true for all positive integer values. This is really useful because it provides an alternative to checking every single number individually. Let's say there's a long domino chain and you want to knock over all of the dominoes which are in this domino chain. There are two strategies you could employ to do this. One strategy would be to remove dominoes one by one until there are no dominoes remaining in the domino chain. The problem with this method is that every single domino must be removed individually, which is very time consuming. A better strategy would be knocking over the first domino in such a way that the first knocks over the second knocks over the third, so that every domino knocks over the subsequent domino in the chain. This allows you to knock over all dominoes by pushing only one. Proof by induction works by proving these two statements. The first is proving that a statement must be true for the smallest possible integer values. These are usually the numbers 1 or 0. The second is that if a statement is true for a certain number where n is equal to k, where n is a number being tested and k represents any number that happens to be true, the statement is also true for number k plus 1. K is what's called an arbitrary variable, which means that it's not bound to any particular value and can take a multitude of values at the same time. Let's say we have proved for a certain formula that when n is equal to 1, statement is true. And if n equal to k is true, then n equal to k plus 1 is also true. We know that 1 is a true value because that's what we proved at the beginning. Since 2 is 1 higher than 1, we know that 2 must be true. And since 3 is 1 higher than 2, which is a true value, we know that 3 must be true. This pattern can keep repeating until all numbers are proven to be true. There are 4 steps involved in an induction proof. To show this, we will try and prove that the sum of 1 over r times r plus 1 from 1 to n produces the value n over n plus 1. This can also be written as 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4, all the way to 1 over n times n plus 1. For an example, let's set n equal to 3. 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 is equal to 9 over 12. This is also produced by n over n plus 1 when n is equal to 3. This means that when n is equal to 3, our equation holds. Our first step is called the base case, where we prove that our equation holds for the lowest possible positive integer value. In this case, that is 1. This is done by inputting the lowest possible value into the equation and seeing if this base case holds. We can see that a half is equal to n over n plus 1 when n is equal to 1. Now we need to assume that when n is equal to a certain value k, then n is true for the equation. For any induction proof, we can simply use the template on screen. The next step is called the inductive hypothesis, where we prove that if n equal to k is true, then n equal to k plus 1 is also true. First, we want to write the expression when n is equal to k, and then we want to add the k plus 1 term to both sides of the expression. Our goal is to rewrite the original equation, with the only difference being that all k's are turned into k plus 1. This will make the equation fit when n is equal to k plus 1. First, we can multiply the fraction k over k plus 1 with k plus 2 over k plus 2. This will allow us to convert two fractions into a singular fraction. This makes k times k plus 2 plus 1 over k plus 1 times k plus 2. We can cancel out one k plus 1 term from the numerator and the denominator to get k plus 1 over k plus 2, which is what we are looking for. Now we have given enough information to prove that our statement is true for all positive integer values. To show anyone who is reading the proof that we have done, we write, we therefore conclude by induction that the sum of 1 over r times r plus 1 from 1 to n is equal to n over n plus 1. In maths, there are two types of induction, which are ordinary induction and strong induction. There are certain problems which require strong induction, because ordinary induction does not suffice. However, for most problems, ordinary induction can be used. Ordinary induction only relies on one base case. We can see this in our inductive hypothesis step, where we try to prove that n equal to k plus 1 is true if n equal to k is true. However, strong induction might require multiple base cases. In ordinary induction, we prove that if n is equal to k is true, then n is equal to k plus 1 is also true. However, a strong induction proof might prove that if n equal to k is true, then n equal to k plus 2 is true, or 3 is true, or any other constant value. In ordinary induction, we assume that if n is equal to k, the value n is true. In strong induction, instead of assuming that some statement is true when n is equal to k, it assumes that some statement is true for all values where n is less than or equal to k. This provides us with some additional information which we can use to solve problems. Let's say we prove that a formula works when n is equal to 1, and if n is equal to k is true, then n is equal to k plus 2 is also true. This means that we know 1 is true, and since 3 is 2 bigger than 1, we know 3 must be true. Since 5 is 2 bigger than 3, we know that 5 must be true. And this keeps repeating until all the odd integers are proven to be true. To prove that a formula is true for all integer values, we may need to define multiple base cases to cover all possibilities. For this case, if we prove that n is equal to 2 is true, then we can prove that our formula is true for all integer values. We want to prove that any number which is greater than or equal to 12 can be rewritten as a sum of 4s and 5s. For example, the number 19 can be rewritten as 5 plus 5 plus 5 plus 4. Since we are only proving values which are greater than or equal to 12, then 12 would be our base case. For our assumption step, we want to assume that all values which are greater than or equal to 12 and less than or equal to k can be rewritten as a sum of 4s and 5s. We've assumed that we can rewrite any number which is less than or equal to k and which is greater than or equal to 12 using a certain amount of 4s and 5s. If that's true, any number which is 4 greater than a number which can be made using a sum of 4s and 5s is also a true value. This is because that number can be rewritten using the same amount of 4s and 5s as the number we know to be true, plus 1 extra 4. Now we have enough information to prove that any number which is a multiple of 4 can be rewritten as the sum of 4s and 5s. However, to prove that our statement is true for all integer values which are greater than or equal to 12, we need to define more base cases. If we divide any positive integer number by 4, we can get 4 possible remainders. These remainders are 0, 1, 2, and 3. The word mod stands for modular division, where you divide the first number by the second and then jot down the remainder. For example, when you divide 14 by 4, you get 3 remainder 2. That is why 14 mod 4 is equal to 2. If we can prove base cases which cover all these values, then we will prove that the statement is true for all positive integers which are greater than or equal to 12. Since there are 4 possible remainders we can get when dividing a number by 4, then we need to prove 4 base cases. We can see how many base cases we must define by looking at the inductive hypothesis step. Here, we see that if k is true, then k plus 4 is true. This means we need to define a total of 4 base cases. Since we have already proven that this statement is true when n is equal to 12, we need to prove that this statement is true when n is equal to 13, 14, and 15. 13 can be written as 4 plus 4 plus 5. 14 can be written as 4 plus 5 plus 5. And 15 can be written as 5 plus 5 plus 5. Since we have proven all necessary base cases, we can conclude that all numbers which are greater than or equal to 12 can be rewritten as a sum of 4s and 5s. There is a game called 2-Power Nim, and it is played as follows. There is a table, and this table contains 2 piles of matchsticks. Both piles contain the same number of matchsticks, and there is no limit on the number of matchsticks in the piles. There are two players, and the winner is the person who takes away the final matchstick. Players take turns, where they choose one of the two piles, and then they take as many matchsticks as they want from that pile. We want to prove that regardless of the pile size, there is always a strategy for the second player to win. This means that if both sides play optimally, player 2 will always win the game. An example game is shown on the right hand side of your screen. The first player takes away one matchstick from one of the piles, and the second player then takes away two matchsticks from that same pile, so that there are no matchsticks in one pile and 3 matchsticks in the other. Now, the first player could take away all 3 matchsticks from the other pile, instantly winning the game. First, we need to define our base case, where we prove that the second player will win when the pile size is equal to 1. The first player is forced to take away one of the matchsticks from one of the piles, and then the second player can take away the final matchstick from the other pile, instantly winning the game. Now that we've proven the base case, we can see what happens when we increase the pile size. If we increase the pile size to 2, there are 2 possible moves player 1 can make on their first move. The first is that player 1 can take away 2 matchsticks from one of the piles. In this case, the second player can take away 2 matchsticks from the other pile, winning the game. The second case is that player 1 can take away 1 matchstick from one of the piles. In this case, the second player can take away the same number of matchsticks, but from the other pile instead. Now the pile size is equal to 1, and it is player 1's turn. From our base case, we know that in this position, player 2 has a guaranteed winning strategy. Since all possible cases result in a guaranteed win for the second player, we can conclude that when the pile size is equal to 2, the second player will always win. This train of thought can be used to prove that player 2 will always win regardless of the pile size. Using this information, we want to prove that player 2 always wins when the pile size is equal to k plus 1. We want to assume that for all pile sizes k, which is less than or equal to n, there is a guaranteed strategy for the second player to win. One option player 1 could do is to take all the matchsticks from one of the piles. In this case, the second player can take away all the matchsticks from the other pile, instantly winning the game. Another option for player 1 is taking away anywhere between 1 and k matchsticks from one of the piles. We are now in a position where the pile size for both piles is some number between 1 and k, and it is player 1's turn. In our proof, we denote the pile size as k plus 1 minus m, where m is some number between 1 and k. In our assumption step, we assume that for all pile sizes which are less than or equal to k, player 2 always has a guaranteed winning strategy. Because k plus 1 minus m is some number between 1 and k, we can conclude that this case always results in player 2 having a winning strategy. Now we have enough information to know that regardless of the pile size, the second player has a winning strategy.